Concentration and molarity. What is concentration? Concentration is how much solute is in the solution. A common example is to think about juice. You can buy juice concentrates and then add water to make it juice. Depending on how much water you add, maybe it's kind of diluted or maybe it's really strong. The more solute is in a solution, the more concentrated that solution is. And if you can add solvent, such as water, then you would make it more diluted. In chemistry, we measure concentration with the unit of molarity. Molarity stands for moles of solute per liter of solution. Notice that that is not per liter of solvent. Molarity is the capital letter M is used to represent molarity, which can be a little confusing when we talk about molar masses and moles and molarity, but capital M is molarity, which stands for moles of solute per liters of solution. We're going to see that this is used as a conversion factor since it will allow to cancel units of moles and liters. In terms of how we talk about molarity, if we have a solution, we use the term molar, a 1.5 molar solution, or a 6 molar solution, etc. However, we normally write it with a capital M, which is really standing for moles per liter. So when I'm doing unit canceling, instead of writing the capital M, I often write the moles per liter so that I can see my units canceling. To calculate a molarity of a solution, we need to know the moles of solute and the total volume of the solution. If distilled water is added to 10 grams of sodium chloride to make 250 milliliters of solution, what is the molarity? Notice that we're given the volume of the total solution, not the volume of the solvent. So here we're really trying to find the moles, and we're going to divide by the liters. So if we have grams, we can use the molar mass to get to moles, and if we have milliliters, we can use our conversion of milliliters to liters, and then we'll have moles, and we need to divide that by the liters. I've done it all out in one step of dimensional analysis. It looks kind of funky here because there's nothing on top, but that's because we're ending up having to divide moles by liters. If this is uncomfortable to do one without one on the top, then you could do it in two separate steps. Find the moles, find the liters, and then divide the two. But we can see that all of our units cancel here to give us what we want. Our grams of salt have canceled to give us moles, and then our milliliters have canceled to give us liters on the bottom, so that we end up with moles per liter. Try this problem on your own. Pause the video, and then check back for the solution. So we're taking the 23.5 grams of copper sulfate pentahydrate. If you got a molar mass lower than this, remember that you have to add in the molar mass of water times 5 to the molar mass of copper sulfate. So then we have our moles, and then we also need to divide by the liters, so we need to convert milliliters into liters. Here's another type of problem involving molarity. Mrs. Turley needs 500 milliliters of 0.5 molar sodium hydroxide to use for a lab. How many grams of sodium hydroxide should she measure out to use to make the solution? This type of problem is pretty common because this type of math is needed to make solutions. Whenever we make solutions for the lab, we need to know how much solute to add. So we're going to start with the volume here because molarity can be used as a conversion factor. So if we start with molarity, we might not end up with the right units. But if we start with volume, we can then use molarity to cancel the liters to get us into moles, and then use the molar mass of sodium hydroxide to get us into grams. Pause the video and try this problem on your own. I've given you the balanced equation here. Just remember that for every mole of HCl that reacts, it will react with 1 mole of sodium hydroxide. Here's the solution. Once again, we're going to start with the volume of the hydrochloric acid, and we can use the molarity of hydrochloric acid to convert it to moles. We're going to use the balanced equation. 1 mole of HCl reacts with 1 mole of sodium hydroxide, and then we can use the molar mass of sodium hydroxide to get to grams. To actually prepare the solution, what you want to do is you would measure out the grams, such as the 20.2 grams of sodium hydroxide that we just calculated. We'll measure it out on a little white paper. Clearly this is not sodium hydroxide because it's green. Maybe this is nickel sulfate or something. Add some water to the volumetric flask first. Okay, so the volumetric flask would be the appropriate capacity. In this past problem, we specifically wanted an amount of sodium hydroxides to add to a solution. So that doesn't really make sense. But in the previous problem, where we were making 500 milliliters of a specific solution, we would choose to use a 500 milliliter volumetric flask so that we made exactly 500 milliliters of solution. So we're going to put some water in the bottom, and then you're going to add the solute to that water. And that just allows it to mix easier. If you put the salt directly on the bottom, sometimes it's hard to get it all to dissolve because it will stick to the bottom. Then you swirl it to mix as much as possible, and then you'll add water up to that final volume so your meniscus is right at the calibration mark. But as you see, it's not super well mixed right at the top here, so before you were to use that solution, you would probably want to pour it into a large beaker or another container to really force it to mix all the way. Molarity of ions. So sometimes you might be asked to find the molarity of a specific ion within a compound that's involved in a reaction, and we just have to remember that the molarity given is the molarity of the solute, and so therefore sometimes if we're asked for the molarity of a specific ion, we need to remember, well, how many ions exist per mole of solute. So for example, if we had a 1 molar solution of copper 2 chloride, it would also be a 1 molar solution of copper 2 plus ions, since there's 1 copper ion per copper 2 chloride. But if we wanted the molarity of the chloride ions, since there's 2 chlorines per copper chloride formula unit, we would have a 2 molar solution of chloride ions and a 3 molar of total ions, since this would dissociate into 3 ions. So try out a problem thinking about the molarity of ions. Pause the video and try it now. Here's your solution. So we're going to start with the volume once again, convert it into liters, use the molarity, 1.5 moles per liter, to cancel our liters to get to moles of our sodium sulfate. For every 1 mole of sodium sulfate, I have 2 moles of sodium ions. And for a mole of sodium ions, I have Avogadro's number worth of ions. And you notice that this problem did ask how many ions, not how many moles of ions. Dilutions. So solutions often need to be diluted, and we can do that by adding distilled water to solutions of higher concentration to make solutions of lower concentration. These solutions of high concentration are called stock solutions. Stock solutions are what we buy, and we keep them in the lab because we can store them in a fairly small volume because they're highly concentrated. But those highly concentrated solutions aren't necessarily very desirable to work with because they're a little bit more dangerous, and we often don't need that high of a concentration. So to solve a dilution problem, here's an example. Determine the number of milliliters of 6 molar hydrochloric acid that would be used in a dilution to make 500 milliliters of 1 molar hydrochloric acid. So notice, we always have our stock solution of a high concentration, and we normally want to find out how much of that high concentration acid are we going to be using to make a 500 ml of a lower concentration. We're just going to take how much of that stock solution and add some distilled water to get up to this volume at this molarity. But what we need to figure out is how many total moles of that acid do we want in that 500 milliliters of our final solution. So we're going to take 500 milliliters and convert that into liters and multiply by the desired molarity to realize, well, we want 0.5 moles of HCl in our final solution. So if we want if we want 0.5 moles of hydrochloric acid, we need to figure out, well, how much of this 6 molar hydrochloric acid do we use to obtain that 0.5 moles that we want? So we're going to now use the molarity of this stock solution to cancel our moles to find out the number of milliliters. I forgot milliliters right here, but that's what this conversion is representing, 1,000 milliliters per 1 liter. So here we've found out that we need 83 milliliters of 6 molar hydrochloric acid, and that's going to give us 0.5 moles, which is what we want to end up making the 500 milliliters. So actually doing the dilution, from that last problem, we would measure out 83 milliliters of the stock solution. Okay, we would use most likely some sort of pipette that has graduation marks on it, or what we sometimes call a volumetric pipette. And we're going to put most likely that into another volumetric flask of the desired volume. In the problem before, the desired volume was 500 milliliters, so we would have a 500 milliliter empty volumetric flask to use. Okay, and before we put that acid into the volumetric flask, you actually want some water in the bottom, which we'll talk about why in a sec. It doesn't show that here because it's not necessary unless it's an acid, but never a bad idea to have it in there anyways. So if you start with some water in here, add your 83 milliliters of acid, and then you're going to add more water up to that calibration line. So why add some water first before you add the acid? The solvation of acid, so when the acids hit the water and start to dissolve even more, even though they start out as aqueous, it's a very exothermic process. Exothermic means that it releases heat to the atmosphere. So it can produce a lot of energy and it can feel very hot, and that's pretty dangerous. So if you have water present, when you add the acid, the water has a very high heat capacity, which means that it can absorb heat. And so if we have some water in there, that exothermic process, not a lot of energy, you don't feel it in the heat because the water can absorb that energy. But if you put a whole bunch of acid in the volumetric flask and then start adding water, and you didn't have water in there to begin with, every time you add that drop of water, it's going to kind of give off energy, but then there isn't any other water to absorb it. So it's going to get very hot. So the saying is, add acid to water like you oughta. And it's definitely a safer way to make solutions. Okay, I will see you in class.